Okay, let's start. Today we will talk about FPGA. We will talk about more details on FPGA. Um, Back to maybe 5 years ago or 10 years ago, um, CPU was the dominant approach um, to solving a wider range of problems. Um, However, because of the machine learning, deep learning, now people pay more attention on the so-called application specific solution or application specific accelerator. So people design new hardware for one single application, which people believe that's the so-called killer application. For example, again deep learning. So back to maybe 20 years or 10 years, FPGA is just a simple solution to do the circuit level debugging. Because when you design the VHDL code, when you design a hardware, for example, new CPU, you cannot fabricate it first. You prefer to deploy that on some FPGA board to see whether it's you know, can achieve the functional correctness. But nowadays, people believe FPGA is a very power efficient solution for those so-called killer applications. Um, the best thing FPGA can do is the reconfiguration. So you can actually reprogramming the functions and the logics on that board. So in this way, you can implement any digital logic functions. So some FPGA nowadays have more advanced features like the partial runtime reconfigurability. What does that mean? That means that if your whole design requires an adder and a multiplier, so that you can do the so-called multiply accumulation operation. If you only have a very small FPGA board, you can configure the FPGA board as an adder. As a multiplier first. And then when you generate the multiplication results, you can reconfigure the FPGA within a very short time, maybe nanosecond, into an adder, so that you can do the accumulation by the same hardware. In this way, we can save a lot of cost, particularly the hardware cost. And of course, the reconfiguration will introduce more energy consumption. And again, you need more advanced tools to manage that dependency. For example, you need to first configure it into the multiplier and then the adder. You need a software to manage these reconfiguration. To do some scheduling, for example, when to do the reconfiguration, when to perform the computation. And FPGA nowadays also contain analog circuit, including some programmable comparators on I/O, which is designed to be connected to differential signal channels. So you have a lot of free flow circuit on the FPGA board, so that you can flexibly use those interfaces to connect the FPGA board to some sensors, so that you can use this FPGA board for more applications. For example, the IoT applications. And because now we consider the analog I/O or analog sensors, we need, of course, the ADC and the DAC, analog to digital converter and digital to analog converter within the FPGA, so that you can enable these conversions. And we call this system the FPGA with analog and digital computation capability, and then the ADC, DAC we call this system as a system on chip. So we can integrate the whole thing into the same chip. And nowadays, even the FPGA has some very simple ARM core, so that you can perform some sequential computation on those CPUs. I believe this is a very common FPGA setting. For example, if you want to use the FPGA to detect the human temperature is some analog signals. And of course, in that case, you need some ADC and DAC to do the conversion. So this figure shows some earlier FPGA, which is only very small FPGA board. It contains an array of unit cell. The unit cell is a so-called configurable logic blocks. So each is a configurable logic block, and you can connect these blocks by some switch and routing networks. We discuss about such type of FPGA board in our previous lectures. We have a decoder which can decode a lot of inputs, and then we have the real logic part, which is the configurable logic blocks. And we can also configure the switch so that we can connect two of these blocks, any two of these blocks. So this is the earlier FPGA board. The next generation FPGA boards also contain some small blocks of RAMs on the edge, like these. This is because people found that because of the big data applications, you have more data will be fetched from the DRAM to the FPGA board. So somehow you need some buffer or space to temporarily store them. So for the modern FPGA, you have dedicated multiplier, dedicated ARM CPU core. You have a lot of so-called PC blocks in the FPGA board. So for example, when you use a lot of multiplication, instead of configure these configurable logic block, instead of configuring these CLBs, you can directly use the multiplier, which actually fabricated on the FPGA board. In this way, you can achieve a better energy efficiency. You can achieve a higher throughput, better performance, because these are the real hardware on the FPGA board, and these are just some so-called lookup table-based computation. They can achieve low power consumption, but the performance is not good. You can add these components on the FPGA board. For example, some memory. Memory array with different ports, different number of ports. You can also have a ECC code to correct the errors if your application require a lot of high accuracy or high precision. You can also integrate some first in, first out FIFO RAMs, some queues. If you use the FPGA as a digital signal processor, you can have a lot of multiplier accumulators and arithmetic logic units, so that when you have these computation in your applications, you can directly map those operations to these hardware components. In this way, you can achieve better performance. Because of the open source of ARM core, most FPGA integrate at least your mobile phone level ARM core on board. So in this way, they can process some sequential applications. You don't need to pass the data to your CPU, to the server CPU. You can just do the local computation. If the computation is not too heavy. Some FPGA can also support the soft core, which means that the core is specialized, which is designed by some third party. You can synthesize this soft core on the FPGA board by the configurable logic blocks and these hardwares. So maybe the CLB and these hardwares are only a part of this soft core. So this figure shows the architecture of the FPGA. So these are the CLB. These are the I/O. Nowadays you have a lot of sensors, so you need a lot of I/O. These are the switches, programmable switch. You can connect these two. You also can connect these two by configuring the switches. So here is some example. You can implement a AND gate, a flip-flop, a XOR gate here, and then connect them together. And use these I/O blocks also. These are the output and these are the inputs. Again, you need to write your truth table, to these CLBs. For this part of logic, of course, and then try to connect them together. If you do not like this function, you can easily erase all the configurations and change another copy of configuration. You can easily build another copy of circuit on the same FPGA. You can even do that at runtime, because the configuration latency nowadays is really small. It's at a nanosecond level or microsecond level, which means that within 1 second, within 1 second you can finish the configuration, you can finish the computation, finish all the components on the same FPGA board. And the CLB consists of multiple components. Of course, the most important one is a lookup table. It's the LRU. You can actually download your truth table on these LRUs. This is the LRU. And besides the LRU, we also have some carry control logic. you can use these carry control logic to implement some adders or substructures. Recall our carry ripple adder. So if you want to implement some carry ripple adder, you can use this carry control logic here. At the last, we have some flip-flop or latch here, so that you can do the accumulation. You can temporarily store the result for this cycle, and then reuse this result in the next cycle. Unlike our logic design, I believe you can actually configure this flip-flop or latch. You can configure it to make it to level sensitive or edge trigger. So remember the difference between the flip-flop and latch. I believe you can achieve both functions by this small piece of circuit. And of course, if you want to build some large circuit which includes a lot of CLBs, and you can configure this flip-flop as a FIFO shift register. And this is the case for multiple CLBs or multiple CLB slice. So here a CLB contains several slices. This is one slice and another slice. So you can think the whole picture like this. You have a very large CLB, and this large CLB is composed of multiple slices. They have two types of slice. One is logic, the other is memory. So this part is the memory part, the flip-flop and the latch part, and this part is the LRU part, is the logic part. And on the real FPGA, they also provide you some masks. So that you can use these masks to implement some logics. You can choose whether this memory element, this latch or this flip-flop, to use how many LRUs. You can use this one component can use all the LRUs, or one of them, or two of them, or three of them. I believe this selection is made by these masks. You can configure these masks to connect this guy to only this guy, or a lot of several guys in the LUT lookup table here. And eventually, the truth table of your logic need to be written into the configuration memories. And the configuration memories also hold the output of the truth table entries. So the internal signals connect to control signals of masks to select one value of the truth table for any given input signals. So for example, this actually the output of your truth table, and they are stored in the configuration memories. You can use these masks to select one of them, and these are the inputs. And these inputs are also the input for the truth table. For example, you have a SAB. Here you also have the SIB. When I, apply the inputs on this mask trace here, I can select the data entry. This is so-called the lookup operation. When I apply the input here, I can look up this entry. I can select this entry and connect this entry to the Z, which is the output, the real output. And here we introduced the so-called LUT-based RAM. So the LUT can be served as a RAM. And each lookup is actually a read operation. And we also have an address decoder here, which can help you to do the write operation. For example, you want to change the truth table, you can enable the write operate signal here so that we can actually change the values in these configuration memories. And we can use some smaller array to form a larger memory. So in each CLB, at most we can have 64-bit these configuration memories, which means that we can choose one of the 64-bit. So that's what happened in the CLB part. Another very important component on the FPGA is the switches, is the routers, is the interconnections. Of course, they are programmable, reconfigurable. The simplest switch is something like this. We have two wire paths, which I call it A and B. I have a memory here. If I write a 1 here, if this is 1, this is a transistor. I actually enable this transistor, so A and B are the same. If I write a 0 here, then the switch is open, the transistor is open. A and B are now the same. So by write 1 bit, I can control whether A is connected to B. So this is only the simplest switches. For the complex one, we have these switches. The crossband can help you to connect vertical or horizontal wire segments so that you can make the signal to have a turn, to make it a turns, to make it a turn. And this one is actually the broke point here. We can also have a maxer here, which means that we select only one from these 4 and select only one connected to this wire. For the compound one, we can make this part connected or opened, so it's more flexible. But again, this part introduces more hardware overhead because you need at least 6 SRAM cell. Each configuration memory is a 1 bit of SRAM cell. So for the compound one, it has the largest number of SRAM cell. So it's very expensive. But again, this is the most flexible design among these 4 designs. It's actually a combination of these 3 designs. We can also have some programmable input and output cells. for example, the bidirection buffers. We can program this buffer to store the inputs or outputs. So we use some tree state to control the bidirection operation. And we also have a pull up and a pull down resistors. So this is the example of the bidirectional buffer. This tree state control can actually control this part of the buffer, so that it can, generate some data to the output and read some data from the input. So we can use this small component to enable more flexible connections. And we also add a lot of flip-flops here, so that we can support a more flexible timing. We can delay some signals and temporarily store some signals to increase the setup and hold timings. We can also delay the output. So this is a part of the routing network. Because we need to reconfigure some FPGA board. We need an interface to support that. The whole process is something like this. We do the programming on some PC, write VHDL, and then we do the synthesis. We synthesize the whole design into some so-called bit stream. And then we can download this bit stream onto the FPGA board. So the FPGA board can temporarily store those pre-existing bit stream in the ROM, which is a read-only memory, at the very beginning. So at the beginning, you can download your bit stream to the ROM. And then the FPGA will not modify this bit stream. So the bit stream for FPGA is a bunch of instructions. It cannot modify it. So this is so-called ROM, read-only. By following the bit stream, the FPGA can be configured. You can either configure the entire FPGA at the very beginning of the computation, before the computation, of course, and then you can also dynamically partially configure the FPGA. You can only configure a part of the FPGA at a runtime. In order to flexibly support this reconfiguration, FPGA create a lot of modes to support this. In order to configure or reconfigure the FPGA at runtime, you need to switch the entire FPGA board into different modes. And here is an example of the multi-FPGA emulator framework to support a network on chip design and app verification. So this is actually a FPGA board. By this JTAG interface, you can actually control the FPGA into different modes. You can download your bit stream on the FPGA or do some debugging on the FPGA. And the FPGA has a dedicated finite state machine to support this testing or debugging. And during the configuration, you cannot interrupt the FPGA. So the FPGA has to finish the entire reconfiguration or runtime configuration and then to proceed to the next computation. And of course, the larger the FPGA is, the longer latency it requires to do the configuration. Nowadays, people do a lot of optimization to reduce the reconfiguration latency. For example, they can compress the configuration into smaller size. In order to support the compression, we need FPGA have different capabilities. For example, the multiple frame write capability, and the partial reconfiguration interface capability. So, and of course, these capability increases the hardware overhead because you bring more free-flow circuit to support this. So this is the example of a Xilinx FPGA. It's not a high-end FPGA nowadays. It's actually a low-end FPGA board. You can see that this is the chip of FPGA. And this is another chip of the FPGA. You have multiple chip FPGA on the same board. And besides the FPGA kernel, we have onboard memories like the DRAM memory and some SRAM memory here. And all these are the free flow circuit to support these two chips of FPGA. And we can also have a network on chip to connect these multiple FPGA chips. So this is so-called a multiple FPGA based emulation framework. So it's not only one FPGA board. It has multiple FPGA chips. And it's not a high-end one. And here are some parameters for the FPGA. And you can distinguish different types of FPGA by their names. If you have LX in their names, they are designed for general logical applications. If it has FXT, then it's a high performance FPGA board. Even in the same type of FPGA, they have a different version for different applications. So this is the example of a CLB on the real FPGA board. A single CLB consists of two slices. One is for the logic. The other one is the memory part. So it has two slices. One is for the logic, the other for the memory. They are connected by a switch matrix. The switch matrix is a reconfigurable routing interconnections. So every slice contains 4 lookup tables and a wide function of masks and a carry logic and some configurable memory elements. So we can use the configurable memory elements to store the output of the truth table, and then you can use the marks to select which one to read. So this is the layout of the CLB. Any questions? So again, for your own design, I prefer some group can try their design on the FPGA board so that we can have a better understanding on not only the FPGA architecture, but also the procedure to use FPGA. So it's not very straightforward to use FPGA. It's not like a CPU or your personal computer PC. When you turn on the power, you have to do a lot of stuff to actually download your bitstream on that small FPGA board and wait the FPGA to configure itself, and then you can perform your own computation. So I would like to have some group of students to try the FPGA. I can support two FPGAs. One is a middle end FPGA board. The other is a low end FPGA board. I believe nowadays you can spend maybe 100 or 60, even $60 to buy a low end FPGA. For the group which select the Shift CNN or XOR NET as their project. So I recommend you at least try to download your design to some FPGA board. If you are interested in doing this, please write an email to me. We can also even try the AWS on Amazon. I don't think for this small project you will need a lot of hours on the cloud-based FPGA. And the cost, we can cover the cost if you choose to use some AWS FPGA board. Any question? So if no question, we can stop today. Thank you very much.